Hi, my name is Michael Harrison, and I'd like to tell you a little bit about myself and about my research. A brief academic history. I completed my PhD in 2017 with Sergei Tabachnikov, did a 2-year postdoc at Lehigh, working with Don Davis, although one semester I was at MSRI, and currently I'm in my final year of a postdoc at Carnegie Mellon. I'm working with Florian Frick. And given that it's the 4th year of postdoc for me, I'm primarily looking for a tenure track position. A general theme in my research is I get really interested in problems that sound very simple, but upon digging into them, I realize that there are close connections with deep results and deep studies in algebraic topology, configuration spaces, nonsingular bilinear maps, the generalized vector field problem, the immersions of projective spaces. These are all things that constantly seem to pop up in the questions I get interested in. But in general, although I study topology, these endeavors have led me to a little bit of geometry and dynamics as well. So I hope to give a brief summary of the main stuff I'm interested in, and since I don't have very much time, I'm happy to talk about anything in the future, so please let me know. So let me ask one of these simple questions. Does there exist a loop in R3 such that no two of the tangent lines are parallel? Of course, this can't happen in R2. If you have a circle in R2, you'll have a pair of parallel tangents, many in fact. But if you ask this question not for a circle, but for just the real line, you can put this in R2. For example, a parabola has this property. The answer is yes, and I've done my best to sketch an example here. And this thing, although a bit confusing perspective, actually lives on the surface of a torus. You can imagine this as some non-trivial loop on the torus, and as you go around, there's no two parallel tangent lines. So I've studied a generalization of this problem. Given a smooth manifold, what is the minimum dimension you can put this in? Minimum dimension Euclidean space, you can put this in without parallel tangent lines. We call such immersions totally non-parallel, hence this minimum dimension defined as TNM. So this is kind of an analog of the classical immersion or embedding problems. So a few simple statements for the real line, the dimension's 2, parabola. For R2, you can consider the complex map, z maps to z squared, and considering this is a real valued map, or a map in real space, this will give you into R4. The circle goes into R3, but we actually don't know the answer for R3, S2, or the torus. So kind of immediately this question becomes very difficult. But let's say a few things about this which connect this to algebraic topology. If there exists a totally non-parallel immersion, then you can obtain n linearly independent sections of this bundle. This is Q minus n times the tautological line bundle over Rpn minus 1. So immediately this thing is related to the generalized vector field problem. And also, except for certain dimensions, totally non-parallel immersions induce immersions of real projective space. On the existence side, existence comes from non-singular symmetric bilinear maps. If you have one of these, then you can produce a totally non-parallel immersion. Non-singular symmetric bilinear maps also produce embeddings of real projective space. So somehow this problem is related to both immersions and embeddings of projective space. Okay, so we can say a little more about obstructions. If you take a function from M to RQ, define this function on the product, which just takes two inputs and outputs the sum of f of x and f of y. You don't have to think about this geometrically, but you can think about what totally non-parallel says about this. And if f is totally non-parallel, then G will induce an immersion of the unordered configuration space of M into RQ. So now we have some way of computing obstructions to the existence of such things. So after talking about this with Don Davis, he was able to show that the unordered configuration space of projective space of dimension power of 2 does not immerse in this Euclidean space. And therefore, this totally non-parallel dimension is at least this. This is actually extremely strong because for any manifold, a generic map into 4 times its dimension is totally non-parallel. So this narrows down the possible dimensions of totally non-parallel to just this or one above it. So I showed, and this was recently accepted into Advances Math, that every smooth n-dimensional manifold admits a totally non-parallel immersion into R 4n minus 1, so 1 less than given by genericity. And this computes the exact dimension for these projective spaces, which are powers of 2. So this is kind of analogous to the Whitney theorems, where you have genericity for immersions in 2n plus 1, but 2n, and then, but however, there always exists an immersion into 2n minus 1. The proof of this uses some differential topology, the removal of singularities H-principle technique, originally due to Gromov and Eliashberg. So I'd like to briefly talk about one other problem I've thought about a lot. Can R3 be fibered by skew lines? When you cover R3, the collection of lines varying continuously so that no 2 are parallel. Yes, you can. And here's an example. You start with a vertical line and surround it with this family of nested hyperboloids. These are all ruled, so you can cover them individually, and this will give you a fibration of R3 by skew lines. There's another way to think about this. You could start with a hop fibration or a general great circle fibration of S3 and do this central projection to R3, which will send a great circle fibration to a skew fibration of R3. Asking this question in higher dimensions, Ovsienko and Tabachnikov found a surprising result. You can fiber Rn by skew copies of Rp if and only if there exist P linearly independent tangent vector fields on Sn minus P minus 1. So this results to this relates to this famous theorem of atoms. My contribution to this was to study further this space of line fibrations of R3. I had a kind of topological classification showing that the space deformation retracts to the subspace of hop fibrations. And also this led me to a relationship between these skew fibrations and tight contact structures on R3. However, there are many open questions in higher dimensions, and this is still something I'm very interested in. Very briefly, let me mention a few other things I've worked on. Billiard problems, geodesic complexity, which is a counterpart of topological complexity, except that you insist that the paths followed are minimal geodesics, and some Borsuk-Ulam type theorems, and several expository papers in the monthly and Math magazine. Thanks very much for listening. Please let me know if you have any questions.